be feeling you should be with your telescope tonight. In fact, I know some people are with their telescopes tonight, but it's unfortunately going to cloud over according to weather forecasts very shortly, so don't feel too guilty about it. Before I introduce our speaker tonight, I'd just like to hand over to David for a few announcements.
Good evening, everyone. We don't have many announcements tonight, just a few short ones. Just a few events coming up. The first of which is in the new year on Thursday the 9th of January at the Acre Road Observatory. This is our monthly beginners class run by Chris here and Lorna. It runs from 7:30 to 9 PM, and the subject this month is the solar system. The next event after that takes place on Sunday the 20th of January, and that's, again, it's a monthly event in the Observers Group run by Robert. This is a Zoom event, it's online. That runs from 7:30 to 9 PM. And the Zoom link will be sent to throughout the time. And the last event, until the next lecture meeting, is on Monday the 13th of January, which is an ESG public night, a night of public observing. If anyone wants to go, you can check the website, and I think it's also advertised elsewhere, is it on Eventbrite? Yeah, that's fine. So that's the events for that month. There's actually no astro imaging. Obviously, we're talking about Christmas, so there's no imaging group this month. But one event which is taking place in a couple of months is our annual Members' Night, which is the chance for the members to contribute. If you want to, if you've got a short talk on any subject, astronomical, maybe even if you're one of these ones that's got a smart telescope for Christmas, maybe just make your point to show. So that takes, we'll advertise that near at the time and ask for contributions. So look out for that probably next month's newsletter. Then we've also got, I think Robert wants to say a few words about something.
There's two important astronomical events going to happen before I do my talk on the 12th, so some of you might know them, you might not, right? They will both occur on Saturday the 4th of January, and the Mills Observatory will be open for people that want to go up to see it there. On Saturday the 4th of January, there will be an occultation of Saturn, and this will take place in the early evening. It's visible in London, so I'm assuming it is visible in Dundee or Glasgow. I'll try, when I've got a chance over the next days, I'm getting busy at the moment, is to put something, it's in the Sky at Night magazine, I'm sure I saw it in the Sky at Night. And on the same night, the 4th of January, that is the maximum of the quadrantid meteors, which is, it's a meteor shower for a constellation that doesn't exist anymore. And it's one I've had a connection with because many years ago I took part with Robert McNaught at the Mills Observatory, an observing programme to observe these meteors. So that's two events on Saturday the 4th of January that are going to happen before I do the talk the following week. And no doubt it will be, as it normally is on these events, it will be cloudy in Dundee, but hopefully it will be clear in Glasgow. Sweet.
Christmas.
Yeah, that's right.
Hey folks, there's a wee Christmas tree coming up. Something that's not going to happen for 30 years or more. If you take a look out at Christmas Eve, you'll see Orion standing up there. You'll see Jupiter shining bright on the right hand side. If you look to the east on the left hand side, you'll see Mars. Mars is in the constellation of Cancer, near a little cluster of stars, M44, we call the Beehive. It also has another name, its Latin name is Praesepe, the manger. So for the first time in a long time, there's a planet in the manger this year. So go out and have a look, see the boy in the manger.
Yeah, just hope Mars doesn't get stung. Don't want Mars getting any angrier than Mars already is. Here, by the way, here is the calendar. If you haven't got one, there's still a few left. So it's £10. All proceeds go towards the ASG, and in particular, helping keeping ECMO running. All the pictures in it are taken by members of the society, and for the first year, we have some pictures, the very first pictures from ECMO in it. Not the best pictures, that will be hopefully next year and future years. So, we come to the main item of business for tonight, and that is to welcome Dr. Ricarda Beckman. She comes to us from the Institute of Astronomy in the Royal Observatory of Edinburgh, but she's come through a very illustrious path, a computational astrophysics by trade, and she has come to us from Imperial College, then to Oxford, then Paris, and then Edinburgh, Cambridge. Missed up Cambridge, yeah. So she's basically checking off all the great universities, so presumably you'll get to Glasgow at some point.
I'm working my way there.
Yes, and she is going to talk to us about black hole spin. Ricarda.
Yes, indeed. So thank you everybody for coming. I wanted to give you today what turned into a bit of a crash course into one of the things I regularly find myself thinking about. If people ask me what do, I would say I think about black holes evolving over very long periods of time across most of cosmic history, but I specifically think about black holes in the context of galaxies. I try to understand black holes and galaxies. I'm going to go a little bit into today why that's important. And one of the things I think about under this part of this heading is black hole spin. So I thought I'd try to tell you today why that's so interesting, why it's so key to the research I do, and why it's really like a very overlooked part of black holes that maybe doesn't get mentioned enough. So, black hole spin. Black holes, really very simple objects, very straightforward. They can be described by only 3 properties. Each black hole, they have a mass, they have a spin, and they have a charge. But actually for astrophysical black holes, we make it even simpler because they're uncharged. So we just have a mass and a spin. Mass is the bit that we often talk about with supermassive black holes. That's sort of what defines it. It's a very, very massive, very dense, very compact object. It's an integral part of our current model, but also of our current way of thinking about black holes. But the spin is sort of the understudied kid on the block. And I'm going to explain to you today why that is and why that's currently about to change, or really needs to change if we want to make some headway here. So what I'm just a brief overview. Today I'm going to talk about why spin is essential to understanding black hole and galaxies, what the spin has to do with the accretion disk and black hole feedback. This is going to be a crash course in black hole accretion physics. You'll know more than quite a lot of people at the end of this. What do we know about the spin of observed black holes? So what about the spin of real black holes in the universe? And what is the kind of work I do where we try to use simulations to really try to fill in some of the gaps that we can't observe. So, let's start with why I even care. Like I said, I do black holes and galaxies. Why do I care about black holes in the context of galaxies? Well, the first important point is black holes live in galaxies. So the kind of black holes I care about is what we call, I would call it massive black holes these days. They used to be predominantly called supermassive black holes. And these are massive black holes that are, they're sort of black holes in the universe roughly come in 2 categories. There are stellar mass black holes. Those are the ones that sort of formed at the end of the stellar life cycle. They tend to have about the mass of a star, roughly a solar mass is where we'd be measuring it. Now, at the other end of the extremes, we have supermassive or massive black holes, which tend to sort of start at about 1 million solar masses upwards. And the reason they're really interesting for not just as fascinating objects themselves, but for galaxies is because of plots like this. Hang on, I had a pointer, we can find that. This is sort of the motivation plot for pretty much all of the research I do. And what we got here is we got a collection of observations, so these are real black holes that somebody has gone out and measured in the real universe, and they put them on these helpful plots, and what we got is fairly straightforward. On the left-hand side here, we got the mass of the black hole. The higher up they are on this sort of part of the diagram, the more massive the black hole, the less massive ones are down here. And then the other axis is basically the same for galaxies. Massive galaxies can be found here, less massive one can be found here. The quantity is a bit funny, it's the standard velocity dispersion, which is a bit of a funky way of measuring stellar mass, but it basically means the more massive the galaxy, the further to the right in this diagram. And you will notice the black holes aren't randomly distributed. So what we see here is that 2 things we see. First of all, pretty much every massive galaxy in the local universe has a massive black hole in the center. And secondly, there's a very close link between the mass of the galaxy and that of the black hole. And you might say, well, that's pretty obvious, but actually, it's not at all obvious. It's not like massive galaxies have more massive stars. So, And in fact, this correlation is very tight. So this suggests to us that there's something that links the two. The problem is, and trying to understand why that is and how that happens is sort of I'd say the broad context of the research I do. Why the masses of the central black holes in massive galaxies so closely linked to the stellar mass of the galaxy, despite the fact that the black hole makes up considerably less than 1% of the total mass of the galaxy, so it's not like it's actually dominating the mass budget, and it's incredibly small. A supermassive black hole, well, small in astrophysical terms, black holes are sort of defined by being extremely compact. In theory, you can turn anything into a black hole. If you took the Earth and you squashed it enough, about the size of a pea, this big, you get a little black hole out of it. But these objects are obviously much more massive. They're a billion solar masses. So essentially, the black hole contains the entire mass that you'd find in a small galaxy in something the volume of, say, Earth's orbit around the sun. So astronomical units is roughly where we'd be measuring the physical extent of these objects. So if you put that in the center of a galaxy, there's a lot of space left. So it's very hard to understand why this small, comparatively light, in terms of the galaxy, compact object would be influencing star formation throughout the entire of this galaxy, which is what you have to do to get this line. So people have thought very hard about why this might be the case, and they've come up with a simple model of what we call coevolution. The black holes and the galaxies co-evolve. And how does this work? Here's the rough overview of the physics we think happens. You have a galaxy. This is a picture from a simulation I've worked with. What we're looking at here is the whole galaxy. It's not the stars, it's actually the gas, but you can sort of see the spiral structure. So this is a spiral galaxy. It could be any type of galaxy there. And this is just for illustrative purposes, but so you know what you're looking at. In the center, you have a black hole, and within the galaxy, you have these clouds of gas. I've helpfully tried to illustrate them with these little clouds. Some of that gas is what forms the stars in the galaxy. This is how star formation in galaxies happen when galaxies become more massive. But also some of that gas falls into the black hole, which is in the center, attracted by the gravity of the black hole if it gets close enough. As a result, the black hole grows in mass because material falls in. But one thing that happens as the material falls in is that some of that mass is converted to energy and re-injected into the surroundings of the black hole in what we call feedback. This is supposed to illustrate it. It can come in various different forms. It can drive fast outflows, jets, essentially. It can drive winds, which have much larger covering fractions, and it can just emit photons, which are then able to be absorbed by gas throughout the galaxy and essentially heat the gas directly. So this feedback from the black hole interacts with the gas in the galaxy, and it heats the cold gas, which is what was feeding the star formation and the accretion onto the black hole in the first place. The gas supply is gone, so it's the source of fuel for both star formation and black hole growth. Black hole growth shuts off, so there's star formation, and over time, new gas forms and the cycle repeats. So the idea here is that because the black hole converts some of the infalling mass into energy, and that energy is re-injected into the galaxy and able to be distributed throughout it and affect the fuel of the star formation, this very tiny central compact object can influence the evolution of the galaxy on much larger scales than its sort of physical extent or even the size of its gravitational sphere of influence would suggest. So in this way, you regulate both the black hole growth because it shuts off its own growth over time and the growth of the galaxy. And that allows you to sort of essentially link, the growth along this direction and growth along this direction, and would explain, at least to some extent, why the two seem to be so closely correlated. When the black hole is very active, it shuts off both, and then they're both sort of active at the same time. So where does spin come into this? Well, so to understand that, you need to look much closer to the black hole. This is an artist's impression. I wish we had pictures of this kind of thing. So what we're looking at here is the environment of the black hole. So if you go back to this helpful diagram, this is the whole galaxy, right? I've drawn in this black hole not to scale at all. It's tiny. You could not even see it on this picture. So what we're looking at here is like hidden behind the black dot in this. In fact, it's probably so small you still couldn't see it. So we're really looking at the direct environment of the black hole. And what we need to think about here is what happens to the gas as it falls into the black hole. So gas in galaxies exists in nebula, it exists in molecular clouds, it exists just in extended arm structures. It exists throughout the galaxy. But when it manages to make its way into the center where the black hole is, black holes are very steep gravitational wells. And because they're very massive and very compact, they tend to gravitationally dominate the environment. So there's a point when the gas comes close enough, it gets sort of essentially sucked into the gravitational well of the black hole. The problem with, if it gets close enough into the black hole, it will fall in. But the problem is, things in the universe have a tendency to be rotating, so they have angular momentum, and that rotation stops them from going straight in. That's the same effect that stops Earth from falling into the sun, right? We're going in a circle, so we keep going around. The same happens to the gas. As it's coming in, it's got some rotation, and it sort of settles into a circular orbit, essentially. But because it's not as discretized as planets, it sort of smears out into a disk, basically. This is what we call the black hole accretion disk. As the gas gets close, it settles into these gaseous disk structures. This is what this image is supposed to show you. You've got the black hole in the center, and you've got all this wispy stuff around it, which is the gas, which is now spiraling inwards. Often you can have a jet in the center. This is the location of the black hole in the image, and then you've got all this hot gas, which is emitting a whole lot of light. That's supposed to be the light, which is then some of the feedback energy re-injected. So both of these would inject energy. The actual emission from the disk gets radiated away and can be absorbed elsewhere. So that's one way to transport energy away from the black hole. These jets, literally a bit like water jets, but cosmic gas, are injected very fast, so they carry a lot of momentum. They can impact things further out in the galaxy and also transfer energy that way. But to look at the importance of spin, the only actual observational image in the whole talk, I apologize, and this is an astronomical society, we can see these jets. They can travel to incredibly far distances. This is an image of a galaxy called Hercules A, galaxies in the center there. These are the black hole-driven jets. You can see, so in this particular case, which isn't always the case, but in this case, the black hole jets actually completely leave the galaxy and get ejected way into what we call the intergalactic medium, so the gas around the galaxy. So they're very powerful. But to understand the importance of spin in this picture, we need to zoom in into the center. Again, not to scale, but the idea is if you look right at the center, and you look at the structure of this disk as you get closer and closer to the black hole, what happens is you hit a point and the disk just stops, and there's a gap. And the black hole sits in the center of that. That's what I was trying to illustrate here. So what happens is gas comes in, rotates around the disk, keeps rotating. Basically, it does a spiral over time, because the disk rotates, but it also transports mass inwards. So eventually, material hits this inner edge, and at this inner edge, this is what we call the innermost stable circular orbit, ISCO. You can work out from general relativity that there's a point when there's just no mathematically permitted way to keep circling. So there's a point when you just cannot have a stable orbit at all, so the gas hits it and just goes straight in at that point. So what ends up happening is you have this gap, and any gas that reaches the inner edge of that gap goes into the black hole. It passes through the event horizon, and it adds to the mass of the black hole. So this is how black hole accretion essentially works through this disk structure. I'm afraid I've got two equations in this. I've been told that every time you show an equation, you lose half your audience. I'm taking the chances here. But I'll get the most mileage out of these equations I can, so hopefully it'll be worth it. So mass falls into the black hole, but we said earlier some of that's converted to energy. So I want to talk you through because this is where the black hole spin comes in. So what have we got here? We have each black hole has a certain, what we call a luminosity, which is basically an energy injection rate, measured in units of energy per time. It's the feedback energy injection rate. That's sort of the energy output that the galaxy would see. It's sort of the equivalent to say if you look at a light bulb, you can work out its energy output. This is sort of the same idea. And this is powered by the black hole growth, by the black hole accretion. And actually, the way to work this out is very straightforwardly. Einstein, you sort of see there's an mc squared in here, right? So we've got the mass inflow rate into the black hole, which we call here m dot, so the time derivative of its mass over time, the rate of inflow, times c squared, that gives you an energy, because the mass is being converted to energy. So you can see that the energy injection rate, this feedback rate, depends on the accretion rate, so the mass growth rate of the black hole as well. So it's not just that the black hole is active when it grows, the more actively the black hole grows, the more energy it injects. But you will notice there's something else in here, there's this eta parameter in there. And this is what we call the radiative efficiency. And it's essentially a conversion parameter. It tells you what fraction of the infalling mass gets converted to energy, and what fraction goes into the black hole. This is what happens to the rest of it. You basically take a mass budget that flows into the environment of the black hole and onto the accretion disk, and you split it into sort of two pots. Some of it makes it to the center and falls into the black hole, and some of it gets converted in the process and gets radiated away. So the actual growth rate, the rate at which the black hole gets bigger, is 1 minus eta. This is where the other part of the energy goes. If we say 50-50, this would be 0.5. And this is the total sort of mass budget of material flowing onto the edge of the accretion disk. So this is the current black hole mass growth rate over time, and this is the exact same at the top there as I've got there. Minus the c squared, because here we're sticking with mass, right? So here we convert into energy, but this bottom row, it's mass here and it's mass there. And the radiative efficiency is where the spin comes in, because the value of this parameter here depends on black hole spin. So the spin of the black hole, the rate at which it is rotating, determines what fraction of the energy it converts or emits. It also, and this is a little complicated, depends on this type of accretion rate, which is making the whole thing considerably more complicated. But basically, so you're beginning to see how the black hole spin plays into this whole sort of picture of co-evolution between black holes and galaxies. So essentially, to some extent, that if you have a certain amount of mass going into the black hole, the spin is one of the most important ways to determine how fast the black hole is growing along this axis, or how much energy injects in this, or how much it is sort of essentially slowing down growth of the galaxy along this axis. So it determines, to some extent, not directly, but it will have an important impact on the slope of this. So if you have very fast growth rates, for example, you would end up with a very different rate here. Like I said, so globally speaking, this black hole mass accretion rate, this is the rate that flows of the black hole accretion disk, depends predominantly on black hole mass. Bigger black holes have bigger gravitational potentials, they have much wider ranges of influence, and they are able to sort of gravitationally attract gas from much larger regions, which generally means they have a more efficient gas supply. But this eta parameter, the conversion depends predominantly on the spin and a little more indirectly on the mass. So why is it that the spin determines this conversion rate? Well, it turns out that this inner edge of the accretion disk is strongly determined by the black hole spin. So a little sort of cartoon here. You can have essentially, well, you can have many scenarios, but you've got 3 broad categories of scenarios. You can have a non-spinning black hole, which is shown in the center here. That's the sort of standard scenario. The inner edge, the inner radius, has a certain diameter for that. And all of that it's purely functional. Because as the black hole starts spinning up, this is what we call prograde rotation. You can see the arrows and the black hole. So the rotation of the disk, so the disk turns in a certain direction, and that's determined by the rotation of the gas flowing in. Say, for example, if you're in a disk galaxy, you could assume it's aligned with the rotation of the whole galaxy, because the galaxy is supplying the gas. And then essentially you've got the black hole that's also spinning in a certain direction. If they are aligned, the black hole drags space-time round its event horizon round. So they're so massive, they're so compact, and they have such a strong gravitational influence that space itself gets pulled along with the rotating black hole, and it creates a region where the space itself is rotating that we call the ergosphere. But the problem is, because space itself is moving, the gas that's in the disk is trying to move in moving space. And it's a lot easier for the gas to rotate with the rotating space than it is to rotate against the rotating space. So if the two are aligned, and the gas is already coming in the correct direction, so to speak, it's able to get much closer and continue on a rotational orbit, and this innermost stable orbit moves inwards. Almost, for a maximum spinning black hole, it technically hits the event horizon, but you can't, for theoretical reasons, have a maximum spinning black hole. But the higher you spin is, the closer the event horizon, the smaller this gap is. It basically vanishes for very highly spinning black holes. The opposite happens if the black hole and the disk are rotating in opposite directions. So that's illustrated at the top here. You can see the arrows going in the opposite direction. Now the gas is trying to rotate against the dragged space-time, and it's having a much harder time of it, and it turns out there's a much larger region where that's just simply not possible for energetic reasons. So the gas then much more quickly falls, or from a much larger radius falls straight into the black hole, and there's basically a much bigger gap. But the energy conversion, a big fraction of that is the fact that the disk is very hot. Hot things tend to give up energy. Things around black holes, accretion disks, are extremely hot, so they give a lot of energy, and disks tend to get hotter the further you get to the center. So a very simple way to understand why this affects the conversion rate to energy is that simply if you're missing the hot center, if you're missing some of the hottest part that's now not radiating, so the whole thing is essentially cooler, so you're giving off less energy grand total, except, Whereas if you have this very hot center, that's a very good way to radiate off some extra energy because it's very hot. So you convert more of the mass to energy if the disk extends further inwards. So what this means, I thought I'd labeled this. So what this means is that depending on the spin, and I've drawn 3 values here, but essentially there's a way to parameterize this where you can say it can be maximally anti-spinning or retrograde, it can be maximally prograde, and it can be anything in between. So this is a continuum, right? I've only drawn 3 examples here, but it's a continuum, it can be anything. And the conversion efficiency is also a continuum, so that's what I'm trying to sort of show here. So what we've got on the y-axis here, which I thought I'd put on, is this eta parameter times 100. So you lose 30% of your energy if you're here, you lose 10% of your mass to energy if you're here. And you can sort of see how it changes with spin. So this is non-spinning, it's in the middle, maximally counter-rotation is down there, and maximally co-rotation is over here. And you can see that the sort of, conversion efficiency ranges from a few percent if you're counter-rotating because you're missing the center, to almost 30 to almost 40% if you're maximally rotating at the other end. So it's more than a factor of 10 difference. From the point of view of that galaxy, that makes a big difference because it means that if there's a certain amount of material feeding onto the black hole in the center, it can experience energy 10 times stronger. Oh, yeah, sorry, there it is. I thought I had it on there. So far so good. The problem is that making understanding the spin evolution black holes so much harder is that accretion disks don't come in one variety. But I've been showing you so far is mostly what we call is sort of this kind of thing. We got one thin, extended, more or less flat disk that's fairly straightforward to model. But people have sort of looked into this. From supermassive black holes, but actually very hard to do, but it turns out black holes work pretty much the same across the mass spectrum. And a really good way to study accretion disks is with so-called X-ray binaries. X-ray binaries are where a stellar binary system, where one of the stars has died and turned into a black hole, and the other star is still there. So what then happens is that the black hole accretes material from the second star, so it has a very nice continuous supply of material, and that material forms a disk around the black hole, and there's quite a lot of them, so they're a very good way of studying black hole accretion disk structure. It's a whole field, and all people who do this have no idea how to do it. But people come up with these kind of diagrams, and I go, well, okay, that's great, but I've just spent all my time talking about this. What about if my accretion disk looks like this? Does this make a difference to the spin evolution and to the radiative efficiency? A little aside, so one of the problems from my point of view is trying to model spin evolution across long periods of time is that this accretion disk structure depends on the accretion efficiency of the black hole. It's kind of hard to tell how efficiently a black hole is growing, so I'm going to have to go down a little aside here. The problem is it's not an absolute value. If I tell you it's growing at, say, 5 solar masses a year, that might be an awful lot for a lower mass black hole, but not very much for a massive black hole, because it turns out there's a maximum accretion rate that depends on the mass of the black hole. Why does that happen? It's again to do with feedback energy. This is a bit of a toy model. The value that comes out of this doesn't actually have a huge amount of physical meaning necessarily, but it's a very good way to parameterize how efficiently the black hole is growing. So here's the sort of toy model. You have a black hole, you have a cloud of gas around it. The black hole has a certain mass. That means it has a certain gravitational force it exerts on the gas cloud, and it pulls it inwards. As it's falling in, it converts some of that mass to energy, as we just talked about, exactly the same way. This energy is radiated outwards, and it pushes back on the infalling gas. The faster the black hole is growing, the more energy it's putting outwards, so there comes up under how stronger that pushback is onto the clouds of gas. So you might think, okay, doesn't that mean they eventually stop flowing in? Yes, and that's exactly what we would expect to happen. At some point, the pushback from the feedback energy is so strong, the black hole kind of cuts its own gas supply off. And you can theoretically work out what that accretion rate would be for any sort of inflow into the center proceeds. And under the assumption from that model, this is sort of the maximum accretion rate. We call that the Eddington accretion rate. If you ever look into black holes, this might start cropping up as a term. The only reason it's important here is because we can basically calculate an accretion efficiency, where we basically take the actual inflow rate, whatever our black hole is currently growing at, in units of mass per time, so solar masses per year would be a typical unit to work with, and we divide it by the Eddington accretion rate, which is a theoretical rate that only depends on the black hole mass and a bunch of physical constants. So it has nothing to do with the actual supply of gas, it has nothing to do with the properties of the gas, it's just a theoretical sort of rate we can work out. And then we divide the two and that just gives us a value. Basically, if I say it's an Eddington ratio close to 1, I would say it's a very efficiently growing black hole. It's something that's close to its maximum growth rate. If the Eddington ratio becomes very small, it's an inefficiently growing black hole, probably because there just isn't enough gas around to feed it efficiently. But essentially, as you can see, this is the Eddington ratio. You can see it crop up again there. So as the black hole starts growing more efficiently because there's more gas around to feed it, the accretion disk structure changes. Because efficiently fed disks take up a different structure. So if they're efficiently fed, you'll have something generally like the picture we had earlier, extended, thinned, well-ordered. And then as the sort of inflow efficiencies onto the black hole go down, the black hole is being a bit starved, the disk starts to puff up into these kind of sort of thick disk structures. And that can make a big difference for how much energy is being converted, because these thick disks work quite differently internally. They're dominated by different processes than the thin disks. So this is the diagram I showed you earlier. I've just given it to you for comparison. There's the helpful diagram to remind you that this is about thin disks. This is the equivalent for the thick disk. Again, we got the labels, yes. You got non-spinning in the middle, maximally spinning on the right, and maximally counter-spinning here. Here you can see, in this model, it went from sort of low to high as the black hole spun up more and more in the line with this disk. But for example, for this model, because it's actually to do with the magnetic field structure of the disk, is very important for this and has a lot to do with how the energy is being extracted from it, rather than being thermal energy being radiated away. You basically get no extraction for a non-spinning black hole. You can get very high values, more than 100% for maximally spinning black holes. So what happens here is you're not just taking all the energy from the accretion flow, you're actually spinning down the black hole because you're extracting some of that rotational energy that's in the black hole to power the outflows. Or if you're counter-spinning, actually becomes more efficient again. So what I'm trying to say, if you're trying to figure out how fast your black hole is spinning up or down, you need to know which state you're in, right? Like, because whether you're here or here is going to make a big difference, even at the same spin configuration relative to the disk. And we know that black holes throughout their accretion and throughout their evolution history undergo many different changes in spin state. So this is a plot from one of my simulations where I asked the question about, these are 3 black holes, we've got a red, a blue, and a green, and I asked the questions, how do these grow over time? So I have a simulation where I model essentially a little chunk of the universe. So the nice thing about my simulations is they're in some way can be very visual. They're like a little 3D cube of the universe with all the galaxies in it that live in that little period, little cube. And I try to simulate the galaxies and the relation between galaxies and the content of the galaxies and how that evolves, including the black holes, because I really want to know how the black holes evolve and how much gas is being fed into these black holes over very long periods of time. So for this simulation, it ran for about 5 gig years. That's not quite half the age of the universe. And you can see the black holes I modeled here, they started at about 10,000 solar masses, and then they grew over time as I modeled their accretion, and they grew to sort of 10 to the 7, so 10 million or so solar masses for the most massive one. And over that time, I checked, one of the things I was interested in is when and how did they grow? Did they grow steadily? Did they grow in bursts, where they grow very efficiently for a while and then not at all? And that sort of turned out to be the case. So this is the Eddington ratio. And you can see it's 1 at the top here, and then it goes down to a very small value, 10 to the minus 12. There's a lot of zeros in front of your zero, in front of your dot. And you can see each black hole, there's no real pattern, well, there is in this particular case, but there's a lot of change going on. And essentially, if a black hole is above this grey line, for a period it'll have a thin disk, if it's below, it'll have a thick disk. And all the black holes here undergo evolution, so they have phases where they're very efficiently growing, probably having supported by thin disks. Then they have phases where sort of things die off, no gas around, something's happened to the galaxy, and then they kind of pick up again. And these ones then continue growing, but you can also find examples where it then starts dying off again. There really is no pattern in the universe. Well, there are some patterns, but for an individual black hole, it's very hard to predict when and how it's going to grow. Sorry. So that means that from my point of view, I need to think very carefully about when and how the black hole is growing and how it is going on. So I've sort of tried to explain, I've sort of tried to make an argument for why spins is so important in this picture, because it's to do with this conversion efficiency. And I've also tried to explain, so this, when I said depends on sort of, and then it depends on the accretion disk that's staying. So you now know what I mean by this sort of arrow here. Okay, so this is the theory for why we care about the spin of black hole. We care because it lies in the end at the heart of this link between black hole and galaxies, and we care about this link between black hole and galaxies because it's probably one of the determining factors why quite a lot of the galaxies around us today look the way they do. So, in today's universe, if you try to model galaxy evolution, given our current understanding of how stars form, how stars evolve, how stars die, how gas collapses, of gravity, of cooling, if you tie everything we think we know together, and we run the simulations to look at the resulting black distribution of galaxies, and we don't put this in, we don't put in the black hole feedback, what you end up with is galaxies that are too massive in comparison to the real universe. So we don't get out what we see. If you do put this in, you get a very beautiful match. So we think this is a really important, one of the really important mechanisms that shape galaxies over very long periods of time. And the spin sort of lies at the heart of it. So far, when people have been doing these kind of simulations, and including this, spin has typically not been modeled. The reason is that it turns out we don't actually know a lot about the real spin of real black holes in the universe. Everything I showed you so far comes from mathematical, theoretical models, because this is a regime that's incredibly difficult to tackle observation in, and get a feel about, what this is really like. People have tried. In the last few years, this is a review from 2020 that's picked up sort of pretty much what we know about the observations of real black holes. I should add here we have probably tens of thousands of mass measurements of black holes by this point. This is probably all the spin measurements we actually reliably have, and there's maybe 25 points on this. And if you look at it, actually, it's even worse, because we've got two types of observations here. So what we've got is on the y-axis, is the black hole spin, from non-spinning to maximally spinning. They've kind of conflated counter and co-rotating, because they have no idea. And on the x-axis, on this axis here, we've got the mass of the black hole in funky units. So these are all very massive black holes. So you need to multiply this in your head by 1,000,000. So this is 1,000,000, that's 1,000,000,000, so the masses. And what we have, 1, 2, 3, 4, 5, 6, 7, 8 actual measurements that are the blue points. Some of them have error bars that are so large they might as well not have bothered, because the only thing they're excluding is like way down here, right? Because you can see that's not very helpful. And then we have these, what they're called lower limits. They're basically saying, for the red points, they're saying we think it's at least that, but it could be anything above it. So depending on where that is also actually quite a large part of the parameter space. Why is it so hard to measure this? Well, the problem is you need to measure the radius of that inner accretion disk structure. That's the only way to do it, really. Or the only way, well, it's not true. There's a few other ways to do it, but that's the most reliable way of doing it. Mass is so much easier. To measure the mass, all you have to do is you have to measure the shape of the gravitational potential. For that, you can have to measure something moving, typically in the gravitational potential, but it can be things that are quite far away, because gravitational potentials extend very far. So, for example, in the center of the Milky Way, this is actually the best measurement we have, but they were actually able to image individual stars orbiting and work out the mass of the object they're orbiting around. That's dream, that only works in the Milky Way, we don't have that data in other things. But we can look at gas rotations, or we can look at bulk stellar rotations, and measure rotational velocities, and then work out the mass that must be at the center causing that. It's hard, but it's doable, because you can probe a fairly large region of the galaxy and take an estimate. For spin, it doesn't help at all. The outer structure, none of that is affected by the spin. The only thing that the spin changes is the structure right near the black hole. So you really have to find a way to measure the structure of the inner accretion disk. It's very difficult to do. There are a few ways that people have found to do this, and probably the most reliable at the moment is what's called reflection spectroscopy. So the idea is, like I said, the disk is very hot, and it emits, for those of you familiar with spectra, a continuum emission. So it has a sort of certain profile of frequencies it emits. The problem is it's continuous. If we want to measure rotation of anything, we ideally want features that we can specifically identify, so-called emission lines. Because we know where the emission line is or should be, and emission lines that are rotating get broadened. So the broader the line, the faster it is typically rotating. So if you have an emission line, figure out what it was supposed to be, measure its broadening, you can take a punt at how fast it's moving. If you then have something close to the black hole, rotational speed directly correlates to the radius where you are. So if you know the mass, you know the shape of the potential. From the rotational velocity, you can work out how close to the black hole that gas that was emitting that emission was. So ideally, you want to find some way to measure the rotational velocity of the gas right at the inner edge, because it rotates faster the closer it gets. So the idea is if you find something almost at the event horizon, you know it's highly spinning. If the best thing you can find is much further out, you can take an estimated guess that there's a gap, and you probably have something that's counter-rotating. But it's very difficult to do. People have had a few other ideas to maybe measure spin. None of them are very practical yet. One potential one is gravitational waves. So when you have two black holes, they merge, they emit gravitational waves, and it gives us a very particular signal. It's what we call a ring down. In gravitational waves, it sort of builds up and it has this sort of squiggle shape, and then they merge and then it goes flat. The exact shape of that squiggle depends on the spin. Unfortunately, it depends on the sort of combined spin of both black holes. It's kind of hard to tell which black hole is which, but it's a way to sort of look at it maybe. There are some clever ideas about trying to use these large-scale, no, I don't have the image again, the large-scale jets. If they're driven by spin energy, maybe we can measure it that way. But it's very hard because it's very degenerate with inflow rates, black hole mass, with all sorts of other things. So basically, long story short, we would love to know, but it's really, really difficult observationally to do. So we have a few points. But it's already a lot better than we used to have, so I'm very happy with these. Because these few points, it's not much, but it's the beginning of a population study. Right? There's several points for similar sort of massive black holes. So we're beginning to get an idea. For example, interestingly, there are no points down here. So that already tells us something about the fact that probably massive black holes in the real universe do appear to be at least moderately to highly spinning. With a sample like this, you always then ask yourself the question, is that just because we can only measure the highly spinning ones? Might that be a selection effect? But that's the kind of question where then my work comes in. Because what I can then do is I take all these models that we have about how we think spin evolves, I put it together with what I think I know about mass growth, and I try to predict what my black holes would be like, and then we can maybe get a feeling for whether they agree with the observations, whether they do not agree with the observations, and if they don't agree, then we have to ask ourselves whether it's because of the observations or it's because of the model. Well, it's complicated, but we can at least try to use this to start constraining some of our theoretical insights and see if we can learn something useful. So that's what I do. I look at all the theoretical models, I look at what we know in observations, and I ask myself, how can we try to fill some of these knowledge gaps to understand a little bit more about black holes in the real universe, and to understand a little bit more about how they might co-evolve with galaxies. And do we even care? Does it turn out that they all have the same value of that efficiency anyway, and it doesn't matter? Or does it make a big difference, and we should really be thinking about it? So, how do we do it? Well, first we model the galaxy. This is, like I said, a picture of a simulation of a galaxy. I wish I brought the movie, but I couldn't find it. What we essentially do over long periods of time is we evolve the evolution of this galaxy. We get out, it's like a little movie of the galaxy changing. I've got a movie of one of my simulations on a much larger scale. I'll show you at the end if I've still got time. So we model the gas in the galaxy. We put in the black hole. We have to assume some initial mass and spin because you need to start somewhere if you want to model the evolution. Typically, we just assume it's non-spinning. You've got to start somewhere. It turns out it really doesn't matter very much. Then we look at how much gas is near the black hole in the simulation. So that gives us an estimate how efficiently that black hole is growing at any one point in time. So we can estimate the accretion rate, which is the rate of material flowing onto the black hole accretion disk, basically, and its Eddington ratio, which we need to decide about the disk model. Then we use theoretical models, analytic models, where people have sat down and tried to work out what happens to material as it flows in the black hole in certain conditions, which is where all these assumptions about the disk stuff I told you comes from. We pick the appropriate disk model, we work out things like the eta parameter. You know, we have the kind of plots I showed you earlier where you can essentially, you can look it up for, so if you know your spin and you know your model. And we have similar plots to figure out how the spin of the black hole is changing over time, because it turns out some disks are better at spinning black holes up or down, whereas than others. Same as for the eta parameter, you get very similar looking curves. I didn't bother showing them because the details don't really matter. We work out the energy being converted for the galaxy. We update how much we think the black hole grows. So if you have a mass of the black hole and then you have a growth rate, you can work out how much bigger it would be after a certain period of time. We work out the energy injection rate for the galaxy. Let's go back before I can build everything up again, hopefully. Yeah, You re-inject the energy into the galaxy, you evolve the whole thing forwards, and you do it again. And you do it again and again and again, until the period of time you think we have covered is long enough to model the kind of periods we're interested in. In my case, that's giga-year timescales, because I want to know the only observations we have up in the universe today, but the spin has been evolving as long as black holes have existed, which is since the early universe, something like 12 billion years ago. I don't know, to skip through this, apologies. What do we get out? What we get out is curves like this. So what we have here, age of the universe on the bottom axis in giga-years, so local universes, it didn't quite make it to the 13.6 where we're at today, but you can sort of see we're getting very close. We've got 5 black holes here, 5 each is a colour. And if you remember the mass plots from earlier, you'll notice the first complication with spin, mass always goes up, spin has a tendency to go both up and down. I assumed all black holes start at 0 spin, so the fact that they're all at nothing here is an assumption I've put in, but you'll notice they all very quickly spin up, so it turns out it doesn't matter at all. I could have started them all up here, they would have looked pretty much the same today. And then they evolve over time. Sometimes not much is happening, it's usually periods when they're not growing in mass very efficiently, they're just sort of sat there, and then they have times when their spin changes quite a lot. One thing I didn't touch on yet is another way to grow a black hole in mass is through a black hole merger. Essentially, you take 2 black holes, you smash them into each other, you get a bigger black hole out. But if you're doing this kind of thing, you need to ask yourself, well, what about the spin? And it turns out there's a way to analytically work out if both black holes are spinning, what the spin of the merged black hole would be, so we do that. These markers are sort of the occasion when that happens, and you notice in quite a lot of them it can produce these jumps. So this purple black hole, for example, not much happened to the spin, it merged with another black hole and then its spin jumped up. So it's something that we need to think about if we want to know what the spin of that particular black hole is today. And then I look at these so I try to do population studies as well. You'll also notice I don't have infinite number of points. It turns out doing simulations is also really hard, but we do our best. So in my case, so these are the observations. In fact, these triangles are what I showed you earlier. The plots, the red and blue plots we had earlier, it's the same kind of plot essentially. You've got black hole mass system, slightly less stupidly labelled. I managed to put all the orders of magnitude on my axis. And then you've got 0 to 1 on that, highly spinning up here, non-spinning down there. I've put another couple of observational samples on here. These crosses are where people basically try to use the jet power from observed jets to estimate black hole spin. They were very enthusiastic. Everybody else was quite dubious because it's really uncertain. I didn't bother putting error bars on this because you wouldn't have seen anything. And then there's another sample here from somebody who used a similar sort of technique that is reasonably reliable, but also contested. So basically I tried to collect all the observations we have on here, but they are very varying quality. These downwards pointing triangles are by far the best. And then I tried to compare my simulated black holes, which are all these colourful dots, to what we have in the real universe. The first thing you'll notice with this is the problem is where my black holes mostly are, we don't have any observations, and where we have the observations, I didn't have a lot of black holes. But I had a few, and the ones I did tended to agree well. I, for example, agreed there aren't any black holes down here. So that already tells us something that it probably isn't entirely wrong. Hopefully it tells us that it's not entirely an observational effect. So it's not just that we can't see real black holes down here, it looks like they actually don't tend to exist in that space. Massive black holes appear to be spinning. Yeah, perfect. This is a different simulation, also a project I was involved in, where we looked at even more massive black holes. So you'll notice my black holes sort of there. I had a couple up here, but mostly I'm looking at individual points sort of above, massive black holes. I only really had a few in this one. This one had a lot more, but they did a much worse job modelling them. I say this as somebody involved in the project. Because it was a much earlier attempt, so we hadn't really built a lot of the understanding of the complexity that goes into these models. But what they found is they had a lot more massive black holes, and they actually, interestingly, even with the simplified model that they were using at the time, started producing some of this downturn. So we have the observations in grey, and you can see that if I ask you, does it go down in this direction, you would probably say, yeah, probably. Like there's not much up here, we don't know, because there's a lot of big crosses and not a huge number of points, but it looks like it might be the case that as you go to even more massive black holes, spin starts maybe dropping again. And the simulation seems to suggest that as well. It wasn't a strong signal, but there was certainly a hint of a downturn at the massive end. So that's something interesting to maybe look into further with better samples. The other thing we looked at is I then start asking more detailed questions. I asked questions like how much of it is the gas accretion, how much of it is, say, brief periods of very efficient accretion, or in this case, how much of it is, for example, black hole mergers with other black holes. So here I tried to figure out how much does the spin of the black hole change when it merges with another black hole. So I've collected all the occasions when black holes in my simulations merge, and I've checked the spin change, and how much that spin changes will depend on the properties of the two black holes before merger. So it depends on the population you study. And what I, for example, found is for lower mass black holes, so these sort of black holes are set in this blue band, when they're just sort of fairly newly formed, they can make a huge difference, right? They can, change the value of their spin by plus or minus, half easily on that axis. Whereas as they get more and more massive, the difference actually becomes smaller and smaller. So for the most massive black holes over here, yes, there's maybe 20% in there, but you don't get anything sort of at the extremes anymore. Most of them are actually close to the middle line, which is basically no spin change. This is partially because massive black holes are more likely to merge with another black hole that's much less massive. So you get the biggest effect when the two black holes have the same mass, because they're both bringing in a lot of rotational energy. And so they're really kind of equally contributing to the spin of the final the remnant black hole, the one that's formed in the merger. Whereas if you have one very massive one and one light one, then the massive one kind of already dominates the rotation, so the change isn't so big. But basically what we're learning from this is that the early evolution might be very importantly affected by mergers, when most black holes in the universe were much lower mass. And the late evolution is probably mergers aren't so important, so it's probably more driven by the gas accretion that happens at these times. And then it starts opening up all sorts of interesting other questions. So one of the abiding puzzles in my field, and something that I actually started doing my PhD on and I'm still working on, is the question of what we call the first supermassive black holes. So the problem we have at the moment in astronomy, and it's a good problem if you're an astronomer, is that we've got this new fancy telescope, the Giant Space Telescope, that's allowing us to look further back in time than we've ever been able to before, and we're able to study black holes and galaxies when the universe was very young, about 1 billion years old. We're finding all sorts of interesting things, but one of the puzzling things we're finding is that we're finding very massive black holes. That's a problem because if you remember the plot I had earlier, I had these long evolution histories. It took my black holes in the simulations 5, 6, 7 gigayears to get to the kind of masses where we'd say that's a supermassive black hole. When the universe is only 1 billion years old, these black holes must have grown extremely fast. Now, one of the things people have argued in the past is that maybe it's because they have essentially no spin. If you have essentially no spin, you're basically creating very little energy because your conversion efficiency, if you remember this slide, is very, very low, right? So, I think I've got the equation now. Almost all the mass that goes onto the black hole ends up in the black hole, and you're generating very little feedback energy, which means that heating effect and blowing the gas away and all the rest that sort of cuts off the gas supply over a long time basically isn't happening. But now, for example, we're beginning to see that massive black holes tend to be highly spinning. That's difficult, right? Because that pushes you on this diagram up here. Basically, we didn't know how this was going to happen. It's just got even harder if you start thinking about the spin in this context. So we're going to have to keep thinking and puzzling on this problem, but I think the spin will have to somehow play a role in it. And this easy way out where we just say, well, maybe they were all low spin. I'm not saying it's impossible. Maybe the early universe was different. We don't actually know. We can't observe the spin at the time. But it's certainly, you'd have to then make an argument for why it was different to what we see today, which is, opening up a whole other kind of The other kind of questions I ask with my simulations is things like, does it actually matter for the galaxy? That if you properly think about spin, or can we just ignore it? So what people used to do before they sort of had any sort of observations of spin really, and people started trying to build these spin models in and try to understand how spin evolves over long periods of time. So you had to assume something for this East parameter. We were always, as far back as we were doing galaxy scale simulations, pretty much doing the energy injection, so you have to somehow figure out what fraction of your accreted mass is being converted. Typical value people tended to use was 10%. There were some arguments for this, they were very reasonable arguments. It's not terribly wrong. But if you actually look at what happens in my simulations where I do model the spin, you can see, well, 10% isn't terrible, but it's also not 100% what I would go for given the data I have. Especially for the massive black holes, we tend to be closer to 20 or 30%. So what that's telling me is that in a classical cosmological simulation where we're not modeling spin evolution, we tended to underestimate the feedback energy received by galaxies by a factor 2 to 3. because we were putting too much mass in the black hole and not enough into the feedback. So maybe this is something we need to rethink. This is fairly new work. You can tell the paper's from last year, so we haven't actually got around to doing it, but it's something we'll be doing in the future. And it'll be very interesting to see how our understanding of predicted galaxy populations changes in this case. So I think then on time, that brings me roughly to the end. Like I said, it was a bit of a crash course in black hole spin, black hole accretion physics, and the kind of things I think about on a daily basis. Conclusions: black hole spin is integral to black hole growth and black hole and galaxy coevolution. Oops, misspelled that, my apologies. It's all about the inner accretion disk. That's both what makes it so fun and what makes it so hard. Measuring black hole spin in observations is hard. Modeling black spin in simulations is possible but complicated because you end up stacking models on models on models. From the work we've done so far on both ends, it appears that massive black holes tend to be highly spinning. We really don't know anything about lower mass black holes yet, with enough certainty for me to be willing to make a statement. And we've only just begun to understand black hole spin, and we are opening up plenty of related interesting questions already. I've thrown up a few, I would say, keywords at the bottom here in case I have huge amounts of time left and I want to keep talking, or one of these twigs your memory and you want to ask me about it. But otherwise, I'm just going to leave it here and open the floor to questions. Thank you.
Thank you, Ricarda, for bringing that cutting-edge research to us here tonight. I didn't mention at the beginning that this, and I should have done, it's my fault, this is the John Brown Memorial Lecture, and there is a connection here in that the person who taught me about black holes and accretion disks was John Brown. And John Brown's supervisor was Peter Sweet. Peter Sweet's supervisor was Sir Fred Hoyle, and his supervisor was Sir Arthur Eddington, whose name you would have heard during this talk. So there is a connection. Also, a more tenuous connection is anyone older members, probably only, remember the Greens of Paul, the Greens Playhouse, which is what, that was connected to Robin Green, and Robin Green showed me how to derive this Kerr metric as an undergraduate, which is describing spin and the ergo
spinning black holes. Yeah.
Yes. So there's another connection there, very bright.
All entirely intentional.
Yes. I remember Robin Green. Yeah.
So wait, I think it's still alive actually. Yeah. Questions for Ricarda? Who's got the first question? Rory.
The magnitude of the spin of a black hole from 0 to 1, is that dependent on maybe like a ratio between how fast the accretion disk is spinning and how fast the black hole is spinning? Is it relatively still light? What actually determines the number?
So the number, it's a little bit like the Eddington ratio in the sense that there's a theoretically maximum spinning rate for a black hole that depends on the mass of the black hole. So there's a way to determine it in sort of physical units, so to speak. We tend to say ourselves the faff and divide the actual black hole spin by that theoretical maximum, which is why it always comes out between 0 and 1. So it's relative to its own maximum spinning capacity, if that makes sense.
Robert.
You showed a slide at the beginning about rotation of black holes, right? So I know what a retrograde is, but there was one I thought, was it porograde? It was a thing I'd never heard of before. What does that mean?
It basically means in the same direction.
Right.
So you can have the disk and the so essentially one of the things that's very interesting is all the pictures I showed you here today show the sort of they show them sort of nicely aligned. You're saying they're either in the same direction or the opposite direction. Actually, the spin of the disk doesn't need to have anything to do with the spin of the black hole. They're both, if you think of them as sort of arrows, they can be at any angle. They can be counter-aligned, they can be aligned, and they can be pretty much anything in between. So yeah, prograde is the term we use for perfectly aligned.
Right.
Oh, I think I've just generated my own personal black hole. My head is spinning. Can I have some?
I know that feeling.
In the talk, you were talking about the fact that the black holes radiate energy.
Yeah.
Were you including in that statement the jets or not?
So yes, I was. So the jets is one of the ways that. So when I talk about energy conversion, I generally mean all forms.
Right.
In fact, I think I have some backup slides where I try to go through some of them.
Yeah. So it's the jets that fascinate me. What what causes the jets, and it seems to be some sort of link to that efficiency rating we talked about.
Yes, indeed. So let me see if I got that. Okay, I don't know if it's actually helpful in this particular. So the theory behind, it's one of the things where we have a well-established, well-accepted theory, but there are people who don't think it's the right one because we're not actually 100% sure. So the going theory is that what happens is that as the black hole is spinning, the accretion disk, as I explained earlier, it's easier to co-rotate than counter-rotate. So the accretion disk actually extends into the region where the space-time is being dragged. And it happens predominantly in these low accretion states where the disks puff up and they have a lot of magnetic fields in them, which thread the disk. So what ends up happening is the magnetic fields get dragged with the material into the black hole. And as the black hole in this inner region of the ergosphere all spins, they get wound up tightly. And that requires energy. There's material being created basically at the base where that winding up is tightest, some of which is ejected at very high speeds. So this winding up of magnetic fields, because it threads the black hole, can extract energy from the black hole because the fields are a certain stiffness essentially. So the jets are being launched from that rotation of the black hole in the disk and that whole inner region. That's a very sort of dumb in the sense that that's my understanding. Somebody who really knows the field would probably tell me that's highly simplified, but that's how I think of it. I think of the field lights being wound up. In fact, I think I have the image for it when I tried. No, I took out it.
So that means then, maybe I'm misunderstanding this, that the black hole isn't actually taking anything into whatever the black hole is, to the other side of it, if you like. It's all being brought back into our own universe, is that correct?
So I think of black holes as sort of one-way, like this idea that it connects to somewhere else in space-time, or is that what you're thinking of?
Yeah,
I think of black, so from my understanding, or from the way I deal with the black hole, and there seems to be, it's sort of like a pocket of space-time, spherical, contained. Anything that goes in never comes back out. Okay. That's sort of the definition of a black hole.
Alright, so everything you've been talking about here is by no means all of the energy that's falling into it is re-radiated into our...
No, and it's not coming out of the black hole, technically speaking. It's to do with how material behaves very close to the black hole.
Yes.
So you have an inflow of matter, which also means energy because E equals mc squared, onto this region close to the black hole, and as it is falling in, a certain fraction of that gets redistributed to the galaxy.
Exactly. All your models are a fraction of it.
It's always a fraction, less than one, less than, it can be realistically 10% is a typical value, can be 30%, can be basically nothing. It can be, so it's always a fraction of inflowing matter, and there's always some that ends up in the black hole after all. And once it's in the black hole, it's gone. That's gone from the energy budget, if that makes sense. It just adds to the mass, which is now slightly bigger. So you've got a slightly bigger black hole and some energy being raised.
But we still don't know what it's really...
What happens to it once it's in the black hole?
So we're in the same situation as, say, 15th century cartographers were when they put a southern continent on the bottom of the Earth because there had to be one there to balance what's the...
Yes, we don't know. Yeah, I mean,
and then they do dragons on it.
Yeah,
so that's the same thing.
I mean, a big problem we have with black holes is that it kind of sort of is at the clash of two of our main theories, right? You have a lot of mass, so it's general relativity, and that's perfectly fine if you're trying to figure out what happens around the black hole, for example, because the length scales are still quite large, and we're talking astronomical units, the size of the orbit of the Earth or something. But as the material falls inward, as far as we can tell, it just keeps falling. The event horizon is a sort of theoretical point in space. It's not actually a surface. It's something that material passes through and then you can't see it anymore. So we don't actually know what happens to it. Presumably it keeps falling inwards. Something must happen, it reaches the center, but as it goes to the center, you end up in a situation where you have a lot of mass, general relativity, in a very small volume, quantum physics. We don't have a theory that covers both bases, so we don't actually know what happens. And we can't check because we can by definition not look in, because no light can escape a black hole. So that's our big problem. It's okay from my point of view because I am predominantly interested in what happens around it. And I treat them basically like a ball, which is a bit, a very comfortable way. So I let other people worry about what happens inside, but we don't actually know.
Thank you.
Any other questions?
I was going to show that Hawking radiation, is that gone?
No, it's not gone. It's not so much a concern for my black holes, because the predicted rates, so Hawking radiation is essentially a way to break what I just said. It's a way to extract mass from a black hole through a funny phenomenon where you effectively have a pair of particles being created just at the horizon, one goes in, one goes out, but the way they work is you can actually end up having negative energy, which then means you take mass out of the black hole. So in theory, it is a way to slowly evaporate away a black hole. If you leave it to just sit long enough and it emits Hawking radiation, it gets less and less and less massive and eventually disappears. If you actually work out the predicted rates of Hawking radiation for the kind of black holes I think about and compare it to the age of the universe, you very quickly figure out it's not a problem. So the actual shrinkage rate is so small that, you know, they grow so much faster than they would ever shrink that I discount it as important in this context.
So the radiation you were talking about is more conventional radiation that's taking place just outside the...
Yeah, so the radiation I talk about is predominantly classic thermal energy.
Right.
So the accretion disk is very, very hot. Because it's very, very hot, it gives us a lot of heat. The same way that anything that's hot gives off heat. That energy is being, and that's energy, right? And that's energy being carried away.
That's X-rays and gamma rays mostly.
Yeah, X-rays, a lot of X-rays with a continuum. So, and the reason it happens is because as material falls in, it's heated up. So essentially what the black hole does is it takes cold gas at long distances, they fall in, they heat up under the gravitational influence of the black hole, they get compressed and all the rest of it. It makes very hot gas, and then that hot gas loses its energy through classic thermal radiation. So it's that sort of conversion mechanism. Or it drives jets, as we were talking about earlier, and where it accelerates material very fast. Fast things also carry a lot of energy. So that's the other way it converts it.
You've been talking about very large black holes compared to solar masses. How small can a black hole be? Because it must start somewhere.
Yes. So I think in theory, I'm actually not sure if there's a theoretical minimum. Like I said, in practice, it's a question of squashing enough mass into a small enough volume. So the problem is, most of the time, the Earth doesn't collapse into a black hole because the interparticle forces keep the material rigid, right? Like, there's gravity pulling us inwards at any point, but the material is stiff enough to counteract that. So the typical way to make a black hole, that's probably the smallest black hole, is that you have a massive star and it has to have a certain mass for it to work. So stars are normally in equilibrium, a bit like the Eddington thing I was talking about. They have radiation pressure outwards and gravity pulling them inwards. While they're alive and the fusion is going on, there's a lot of energy being generated, so they hold themselves in this equilibrium, right? At some point they run out of fuel and they collapse because the outward pressure goes. This is when they tend to go supernova. But this is one of the situations where the universe creates conditions for a lot of material to collapse uncontrolled very rapidly. But you do need a minimum mass of star to make a black hole, because if you don't, you end up in a similar sort of situation as you do with the Earth kind of thing. You end up with a neutron star, basically, where the particles, the interparticle forces are stronger than the gravitational pull of what's left. So you have a neutron star. You have to have something that's more massive over what's called the Chandrasekhar limit. So there's a minimum to make a black hole. I think what you end up with is a black hole of about a solar mass. So about the mass of the sun. The sun is not massive enough to do it because it will lose material in the process, so if it's already about the solar mass, it's not massive enough. So I think that's practically probably about the minimum. I say that, but then there are people talking about what I call primordial black holes. The idea is here these are black holes created, and this is going to start sounding whack, from quantum fluctuations in the very early universe, way before we have the first stars and galaxies. My understanding there is people talk about planet mass black holes, even particle mass black hole, like, basically as far as I can tell, in that theory it's essentially a continuum, and you can have theoretically pretty much any mass black hole. That being said, that one, as far as I know, is mostly a theory at the moment, so I don't think anyone's ever observed a planet mass black hole.
Very early on in the universe, it would be very, very dense. Could you not then have conditions where any amount of material could fall into a black, create a black hole?
Yeah, so I think there's two things. So there's the mass of the black hole when it falls, because you have to somehow, black holes are very specific objects. Right? They have this event horizon that's bigger than the extent of the matter in the middle. So there's a point when, so something like normal matter, it's still normal matter, but when an object can become a black hole with these very specific properties. That's what we think of as the black hole formation. And then once it's formed, they can start accreting material and become a more massive black hole. So there's certainly an idea that in the so is this about what I showed the observations about the early universe, where I said we have this problem where we see these big black holes early on. Yeah, so this is one idea, and we do think the early universe has worked differently, and we know there's a lot of gas around, because it is the time when galaxies are also starting, so a lot of gas hasn't been converted into stars yet. The problem is, and this is maybe a problem with that model, but our current models, the kind of things I work with, do surprisingly well at reproducing the black holes we see today, the populations of black holes. But they take a long time to build up. So if we try to apply the same model to the early universe, because there's so much going on, the black holes themselves have to grow very rapidly, which then means they're producing a lot of feedback energy, which then slows down their own growth. There's also the fact that the stars are forming and dying very rapidly. So they're in the early universe. So basically, stars have a certain lifetime. The more massive the star, the faster it dies. In the early universe, stars were thought to be much more massive, but that means you have a much faster recycling cycle. Stars form and go supernova, form and go supernova. That means you have a lot of energy injection from the supernova alone. So as far as we can tell, galaxies are hugely active, and it's really hard to keep enough cold gas going to feed the black hole. So most of the gas ends up being very hot, it's being rapidly ejected all over the place, but actually getting it into the black hole, given our current understanding, is really challenging. So we don't really know. But it must happen because we see them. Or well, maybe our observations are wrong, but I'm not going to stick my head out there and say so. But yeah, it's tricky, it's very difficult.
Hello, I have a question. Is it the theory to say which type of rotation will be more beneficial for the galaxy and their bodies within?
So can you repeat that question? Which rotations?
Which type of rotation from the black hole would be potentially more beneficial for the galaxy and their bodies within?
So I guess it depends what you mean by beneficial. So what is the galaxy trying to accomplish? If it's a case of I'm trying to think about which angle to answer that question from. So there are several things here. The first one is to do with alignment. So galaxies, a lot of galaxies can be very thin. Classic disk galaxies, they have a very specific shape, right? They're extended in one dimension, but they're very flat in the other. Now, if you think of, for example, the energy injection is in the form of jets, you can have two main scenarios. You can have a jet that's perpendicular to the disk, and then you probably end up with a scenario more like, well, okay, it's gone now. This is what I'm thinking of. You know, if the jet goes basically straight out the galaxy. As far as the galaxy is concerned, there's not much happening. There's maybe a little hole in the middle, but the energy gets deposited far away from the galaxy. Alternatively, if you can imagine that jet is for some reason reoriented into the galaxy, it'll have a big impact on the galaxy, right? It will hit a lot of that star-forming gas. You could probably sweep up material and drive it out, so you would evacuate a lot of gas in the galaxy. So that would really impact the galaxy, for example. So that's one of the things that I haven't really talked about today, but one of the things I look at is the angle between, say, the galaxy and the spin of the black hole, and how that might change over time, and how that might impact galaxy evolution. And then the other question is whether it's a galaxy that's, for example, so one of the puzzles we have in the observation of galaxies is that all our massive galaxies are no longer star-forming, virtually all of them. They are what we call red and dead, that all the stars are old, which means they tend to go reddish, there's not a lot of sign of star formation, and there's not a lot of gas. But these galaxies came from galaxies that had a lot of gas. So there must have been, somehow we must have gotten rid of that gas, and you need to stop it from reforming, because otherwise they would start forming stars again. And one of the things we think that black holes do is maintain that balance. So every time a bit of gas forms, the black hole turns on, and it shuts it off again. So that basically keeps galaxies what we call quiescent, or not star forming. So I think, so that for example is something where you probably want a reasonably efficient energy injection, right? Because to keep the galaxies so to match what we see, the black hole must be injecting energy, and that's easier to do if the spin is such that that's possible, so highly spinning typically. So that, for example, would align with what we see about the massive galaxies in the universe, which tend to be highly spinning, so therefore would be fairly efficient converters, which makes sense given that we see galaxies tend to not be star forming when they're very massive. Does that sort of help? That's sort of a few ideas of how that might tie together.
Yeah, well, some excellent questions there and an excellent talk. We thank Ricarda once again.
Oh, yeah.